Hello everybody and welcome to Chapter 2, Introduction to Frequency Selective Circuits. Now, what is frequency selective circuits? They are circuits that pass to the output only those input signals that reside in a desired range of frequencies. Many devices that communicate via electric signals such as telephones, radios, televisions, satellites, and so on, employ frequency selective circuits. Now, frequency selective circuits are also called filters because of their ability to filter out certain input signals on the basis of frequency. Now, there are four major categories of filters. They are low pass, high pass, band pass, and band reject filters. So let's start. Filters. And we said there are four types of filters. The first four major categories of filters. The first one is low pass filter. Second one is high pass filter. Third one is band pass filter. The fourth one is band reject filter. Now, in this lecture and in the next lecture, we will discuss the passive filters. And later on, we will discuss the active filters. Now, what is passive filters? Passive, so we will be talking about the passive filters first. Passive means that the gain will not exceed 1. The gain symbol K will not exceed 1. We will discuss deeply the low pass filter, we will analyze them. We will also analyze the band pass filter. However, we will only touch on the band reject. We will not analyze it. Now, in order to solve for filters, let's take a note. In order to solve for filters, we have to convert the circuit from time domain to frequency domain. Now what is the time domain and what is the frequency domain? From time domain to frequency domain. Okay. If I give you a circuit where we have a voltage source, a resistance in series with an inductor and a capacitor. Okay, now this is in time domain. How did I know this is in time domain? Because of the impedance R, inductance L, and the capacitance C. This is time domain. How do you convert this to frequency domain? No, it becomes the voltage source will stay as is, it will be VI. However, the resistance, the impedance will still be R. Okay, whereas the inductor, it will become SL. This is the impedance of the inductor in the frequency domain. And for the capacitor, it will become 1 over SC. Okay, so this is the conversion from time domain to frequency domain. Let me put them in a table. The impedance. For time domain, frequency domain. We have three types of impedances. First one is resistance, inductor, and the capacitor. As we have seen earlier, the impedance in the time domain for a resistance is R, and in the frequency domain it's still R, whereas for the inductor in the time domain it's L, and the frequency domain it's SL. For the capacitor, the impedance is capacitance C, and for in the frequency domain it's 1 over SC. Now, for the impedance for the resistance is a real number, whereas for the other two it's imaginary. Why are they imaginary? Because they have an S. What is an S? S is equal to JW. What's J? J is the imaginary number. J is the imaginary number, which is square root of -1. W is the angular frequency. Angular frequency. Frequency with the unit rad per second. Now, omega is equal to 2 pi f, where f is the frequency in hertz. Frequency in hertz. I hope it's clear. Okay, moving on. In the last series, or in the first chapter, when we discussed amplifiers, I gave you two types of graphing. The first was the waveform, the graphs in time domain. We had the waveform and we had the VTC. VTC stood for voltage transfer characteristic. Now, what was the waveform? Waveform was voltage or current, output voltage, let's say, with respect to time, whereas the VTC, it's V output with respect to the input. Okay. Now let's move on to the graphs in time and frequency domain. Sorry, in the frequency domain, we have a graph called the frequency response plot. Frequency response plot. What is the frequency response plot? It's a plot that consists of two plots. The first one is the magnitude plot. The second one is the phase angle plot. The magnitude plot, or the magnitude, has the symbol of h of jw with a magnitude absolute value. For the phase angle, there's the theta of jw. How can we plot two graphs in one? Let's see. So here's our y-axis and the x-axis. At the x-axis, we will put the angular frequency. On the positive side of the frequency response plot, we're going to add the magnitude, and on the negative side we will add the phase angle. So here we as you can see, we have included the two plots in one. This is the magnitude and this is the phase angle side. Okay. Now, the transfer function of a circuit is the starting point for the frequency response analysis. we will be having a function called the transfer function. What is the transfer function? The transfer function having symbol h of s is equal to the output in terms of s divided by the input in terms of s. This is one form of the equation. Another form of the equation is replacing s with jw. So it becomes as follows. This is the other form of the transfer function. So we can either use this one or this one. Okay, moving on. Now we said that there are 4 categories of the filters. The first one is low pass filter, then high pass, then band pass, then band reject. What are those filters? Now let's start with the low pass filter. Low pass filter, as the name suggests, it passes the low frequencies and the high frequencies gets rejected. If I plot the magnitude plot here, this is magnitude with respect to angular frequency. We need to pass the low frequencies and reject the high frequencies. Now, what defines a low frequency? For example, 100. Is this a low or high frequency? 1000, 1000. Is it a low or high frequency? What about frequency equal to 1? Now, it's unclear, or we cannot define what's a low and what's a high frequency unless we have a threshold. Now, this threshold will be called the center frequency. Any frequency below the center frequency is a low frequency, and any frequency above the center frequency is a high frequency. For example, if I say that omega c is 50, then 49 is a low frequency and 51 is a high frequency. So here, any frequency below omega c will be passed, and any frequency above omega c will be rejected. Now, as we were discussing the passive filters, the maximum magnitude will be 1. As we said, the passive has a maximum gain of 1. The region that gets passed is called passband, and the region that gets rejected is called the stop band. This is a low pass filter. Now, moving on to the high pass filter. Let's break this page into 4 areas. Pardon me. High pass filter. The magnitude plot is as follows. Angular frequency with magnitude. Okay. Now, we said that we need a center frequency to define the low and the high frequency. Any frequency, as the name suggests, high pass filter, it will pass the high frequencies and rejects the low frequencies. The maximum magnitude will be 1, and the area that gets rejected will be called stop band, and the area that gets passed is called the pass band. Let me define the omega c. This is called the center frequency. Okay, now moving on to the bandpass filter. The magnitude plot is as follows. Omega with magnitude. Now, what is bandpass filter? Bandpass filter says that any frequency within a certain range will be passed, and any frequency outside this range will be rejected. So how many frequencies can you guess? How many frequencies do we have? So here we have 2 cutoff frequencies, omega c1 and omega c2. Any frequency between omega C1 and omega C2 will be passed, and any frequency outside this range will be rejected. Now here we have two stop bands and a pass band. Pass band. The fourth type of filter is the complete opposite of the bandpass. This is the bandreject. We also have two cutoff frequencies, but any frequency within the range will be rejected and any frequency outside the range will be passed. This is the magnitude, omega, magnitude with respect to angular frequency. We have two center frequencies, omega C1, omega C2. Any frequency within the range will be passed, outside the range will be passed, and any frequency within the range will be rejected. So here we are having two pass bands and a stop band. Okay, I hope now it's clear the difference between all the different types of filters. Okay, now I will include everything in one table so you can get a complete picture of the first three filters. The fourth filter, we will not discuss it. Let's start writing the table. So here we're having a passive, then general equation, next we have the circuit, cutoff frequency, and lastly the magnitude plot. Let's start with the low pass filter. The low pass filter. What is the general equation of a low pass filter? The general equation is h of s equal to omega c divided by s plus omega c. There are two forms for a low pass filter, two circuits for a low pass filter. The first one is a voltage source in series with an inductor and a resistance. Okay, this is the output. The cutoff frequency for a low pass RL circuit is omega c equal to R over L. Okay, the other form for the low pass filter is RC circuit, where we have VI and a resistance with a capacitor, and the V output is being measured on the, let me fix this, capacitor, and this is the output. Okay, the output measured on the capacitor. Omega c here is 1 over RC because it's an RC circuit. What is the magnitude plot? The magnitude plot is as follows. Now earlier I have showed you the ideal case of an magnitude plot. Let me show you the more realistic magnitude plot for a low pass filter. It's as follows. Let me pick the right color. Let me pick this one. Okay, so it's like this. Here we have the center frequency, omega c. This is the maximum magnitude. We will call it the H max. At the center frequency, the magnitude is always equal to H max divided by root 2. Okay? H max divided by root 2. Now, when the frequency is 0, we get the maximum magnitude, which is 1. If we are having a passive filter, the maximum magnitude will be 1. And if the angular frequency, is infinity, we will have a magnitude of 0. Now here it should be approaching 0. Okay, it's not touching 0, it's approaching 0. Moving on to the next filter, the high pass filter. Let's choose black. The high pass filter. The general equation is as follows: h of s divided by s plus omega c. And the two forms of the circuits in the high pass filter is the complete opposite of the low pass filter. So here we're having a voltage source, a resistance in series with an inductor, where the V output is measured on the inductor. Omega C is still R over L because we are having an RL circuit. Okay. The other form is an RC circuit. Voltage source, VI, capacitor, and a resistance. And the output is measured on the resistance. This is C. Omega C is 1 over RC because we're having an RC circuit. Now the magnitude plot here is H of JW. It starts low, and whenever it hits the maximum magnitude, it starts low. Whenever it hits the cutoff frequencies, the frequencies gets passed. Yeah. I should have chosen purple. Let me change the colors for consistency. So here we said we start low, and whenever we hit the maximum, this graphing is bad. Let me draw it again. So we have to start low, and whenever we hit, this is even worse. But anyhow, you get the point. Okay. So here, at omega equal to infinity, we're getting the maximum. This is H max. Here we have the omega C, the cutoff frequency, and the magnitude at the cutoff frequency is always equal to H max divided by root 2. At frequency equal to 0, we get the lowest magnitude. Okay. Moving on to the bandpass filter. I think this is the worst table you have seen. Okay, bandpass filter. The H of S is beta S square plus beta S plus omega naught squared. Okay. Now, let me mention something. Bandpass filter is a combination of two filters. It's a combination of high pass and low pass filter. Okay. So, and it's the only filter that will consist of the three impedances: the resistance, the inductance, and the capacitance. So this is the circuit of a bandpass circuit. We have an inductor, series with a capacitor, and a resistance. And this is V output. Okay. This is the output. Okay. Now here we do have two cutoff frequencies, but let me write only the center frequency. Here it's center frequency omega naught, which is equal to 1 over a square root of LC. We will talk about this later, I think in the next video. Okay, so this is called the center frequency. Okay? Yeah, center frequency. The magnitude plot of the center frequency is as follows. H of JW. We have the two cutoff frequencies, omega C1, omega C2. Okay? Purple. The graph will start low. Whenever it's in between the range, it will go up to the maximum, and then when it exceeds omega C2, it will drop again. So at the maximum, we're getting, this is the center frequency. We get the maximum magnitude at the center frequency. So here, it's H max. And at omega C1 and omega C2, we have H max divided by root 2. We have H max divided by root 2 at omega C1 and omega C2. Okay? Oh my god. Here we go again. Okay? So at omega C1 and omega C2, we are having the H max divided by root 2. Okay, now notice that the bandpass is a combination of the two filters, low and high pass. Why? This is the high pass, right? And this is the low pass. Now what is this? What's this? Isn't this the bandpass only? See? Okay, moving on. Let me mention something. Now, I said that we are talking about the passive filters. Passive filters says that the maximum gain is 1. Now for all magnitudes, we do have a gain k, but I did not include it in the first place because the maximum gain is 1. Sometimes we do have gain of less than 1, but most of the time it's 1. So if we write a k or we exclude it, then it doesn't matter. But let's write it for completion. So here k is 1 in the passive filters, maximum gain is 1. Let me give you a hint how to memorize these things. Okay, here we have a low. See, it's an L with a low L and then W. L, whenever you see an L, this means there should be an L on the top. Because if you have R on the top, that's a high pass filter. And W, because if it's low, then you are having an omega C, omega, in the numerator, whereas in the high pass, you will have an S in the numerator, okay? I hope this will make it easy for you to memorize it. Okay. How are we going to analyze the filters? Now, most of the questions that will be asked on the filters will be as follows. The first type of question is sketching. Sketch waveforms, sketch VTC, sketch magnitude. Now usually they don't ask for, in an introductory course for electronics, they don't ask for a phase angle. So I will just talk about the waveform, VTC, and the magnitude plot. Okay. Another type of question is the type of filter. When the instructor might give us a circuit, and we have to find the type of filter. Find type of filter. Okay. Another type of question is finding transfer function. Now, transfer function, we said it's the h of s, and they can ask us to find the magnitude and the phase angle. Phase angle. Okay. Furthermore, we can be asked to find the H max, which is the maximum magnitude, and the center frequency. Now, why did I write it in this G format, hierarchy format? Because if we were asked to find the H maximum, we need to note or be careful that in order to find H maximum, we need first to find the magnitude. And at the same time, in order to find the magnitude, we need to find its parent, which is the transfer function. So in this way, it will be easier for you to figure out what you need first in order to figure or to find out the requirement. The symbol for the transfer function is h of s or h of jw, and the magnitude is h of jw with the magnitude signs. Phase angle it's theta jw, h max, and omega c. Those are the symbols actually. Moving on, let's start taking examples. Let's start with the low pass filter. Low pass filter. Let's say we have this circuit, okay, Vi with inductor and a resistance, okay. This is an ugly circuit anyhow, and the question is to find the type of filter. Now you already know that this is a low pass filter, but let's say that we don't know and we need to figure it out. So as I said before, that the first thing that we need to do is to convert it to frequency domain. What happens to the Vi? Nothing, it stays Vi. The inductor becomes SL and the resistance becomes as is R. Okay, now in order to find the type of filter for any circuit, we substitute in two values at omega equal to 0 and at omega equal to infinity. Why do we substitute in these two values? Because here, if we go back to the magnitude plots, let's take a look at the low pass filter. Now at omega 0 we have the maximum magnitude, whereas at omega infinity we have the lowest magnitude. Okay, in the high pass filter at omega 0 we have the lowest magnitude, and at omega equal to infinity you have the highest, which is the completely opposite. So when you substitute in two values, you will get two different outputs. According to those outputs, you can determine if it's a low pass or high pass. And the same thing for the bandpass filter. If you substitute in 0, you should get the magnitude 0, and if you substitute in infinity, you should get also the magnitude 0. Sorry. Okay. So as you can note that for the three filters, you have three different outputs if you substitute in two frequencies. So here at omega equal to 0. Now the question is, where should I substitute in omega? Where do I have omega in the circuit? Now note here that we have omega in both inductors and capacitors, because omega is hidden inside the S. In this circuit, in this example, we have only inductor. Let's start. Inductor, it's equal to SL, which is equal to JWL, J0L, which is equal to 0. Now 0 represents a what? A short circuit. Let's do the same thing for omega equal to infinity. Inductor is equal to SL, JWL, J infinity L, which is equal to infinity. That's a what? An open circuit. Okay, short circuit, open circuit. Now we redraw the circuit. Vi, inductor becomes short, this is resistance, V output. Same thing for the other scenario, open circuit with a resistance. Okay, so what is V output here? V output is equal to V input, because they are in parallel. Here we have no current, and if we have no current, resistance is useless, therefore the output is equal to 0. Let's plot the magnitude plot for this circuit. Okay, so here we have the magnitude with respect to omega. At omega equal to 0, what is the magnitude? Now magnitude is V output over V input, which is equal to 1. How did I get this? Let me do it all over again. Here, let me divide by, if we divide by v input, what are we going to get? If we divide both sides with v input, what are we going to get? We're going to get v output over v input equal to 1. Now this is the magnitude, okay? And it's already positive, there's no minus sign. And let's do the same thing here. We will get v output over v input equal to 0. Now the magnitude is v output divided by v input, which is equal, it's not equal to anything. Let's plot these two values. At omega equal to 0, the magnitude is 1. So at omega equal to 0, here we're having 0, that's 1. So this is the first point. At omega equal to infinity, the magnitude is 0. So at infinity, the magnitude is 0. The only combination that has 1 and 0 at magnitude, at frequency 0 and infinity is the low pass filter. So what is the answer? The answer is a low pass filter. Now we already knew this before, but just to show you how to determine the type of the filter. Now we're done for the first part of that question. Let's continue. Question B. Part B, sorry. Part B says find the transfer function. What is a transfer function? Find the transfer function. Now our circuit was a voltage source, inductor, and a resistance. This is the output. Okay. What is the transfer function? The transfer function is h of s, and we said it's v output over v input. Now you can think of this as a voltage gain, as a way to memorize it. Now where do we start? As I showed you earlier, that whenever we have a gain, we always start from the numerator. We will do the same thing here. We will start with v output. Okay. Now give me a relationship, an equation that relates v output with v input. Relationship that relates v output with v input. Of course, it's voltage division. So it's VI in terms of S multiplied by R divided by R plus SL. The transfer function is V output S VI S equal to R over R plus SL. Now we're not done yet. Why? Because we need to convert or make this form in the same format as the general equation. What was the general equation of a low pass filter? It was h of s, let's see, it was h of s k omega c over s plus omega c, k omega c over s plus omega c. Okay, so here, do we know what is omega c? Now yes, we do know what is omega c because this is an RL circuit. Omega c is R over L here. Omega c is R over L. But let's assume that we forgot what's omega c. Okay? How do we convert this form into the same form as the general equation? Okay? We always focus on the s's. What do I mean by that? For example here, do I have an s in the numerator? No, there's no s. Do I have s in my equation? No, there's no s. So I'm doing fine so far. Let's look at the denominator. Do I have an s? Yes, and its coefficient is 1. Do I have an s in the denominator? Yes, I do, and its coefficient is L. I need to get rid of L. How do I get rid of L? I have to divide by L. So 1 divided by L multiplied by 1 divided by L. What will this give me? It will give me R divided by L divided by R over L plus S. Now this is in the same form as the general equation, and it's correct. Why? Here you go. Why is this correct? Because the numerator is omega c, okay, and we said omega c is r over L, and here we have an s, similar to the general equation. Now, what is the coefficient of the omega c in the numerator? It's 1, which means the gain is 1, which is correct because we're having a passive circuit, passive filter. Okay, we're done for the second part of the question. Moving on to the third part, which is finding the magnitude. Part C, let me write part C. Find the magnitude of the transfer function. Now the magnitude is h of jw with the magnitude signs. Okay, now who's the parent of the magnitude? The parent of the magnitude is the transfer function, right? So in order to find the magnitude, I need to find the transfer function. And we already found the transfer function. The transfer function is h of s equal to r over L divided by s plus r over n. Okay? Now in order to find the magnitude, we need first to put it in the JW form. H of JW. So it's r over L JW plus r over n. Now note that this is still not the magnitude, it's still the transfer function. We only removed s and substituted with replace it with JW. Okay? Now, what are we going to do next? The magnitude is the real value of the transfer function. Now, the transfer function, is this a real number or a complex or imaginary number? It's a complex number. Why is it a complex number? Because it has both real and imaginary parts. Okay? This is imaginary, this is real, and this is real. So it has both real and imaginary. Okay? Okay. How do we extract the real part from a complex number? In order to do this, we need to have some knowledge on complex numbers. Okay? Let me add a page here and give you a brief introduction on complex numbers. Okay. Complex numbers. Complex numbers. There are two forms to represent a complex number. The first form is the trigonometric format. This is supposed to be t. Don't ask me how. Okay, trigonometric format. The other one is the phasor format. Okay? Now, what is the trigonometric format? The form of the trigonometric format is a plus, this is the simple form, a plus jb. A is the real part and b is the imaginary part. Why b is the imaginary part? Because it has j accompanying it. Okay? What is the phasor format? It's n equal to c e j theta. What's c? C is the magnitude. Okay? C is the what? Magnitude. And theta is the phase angle. So in the question here, let's go back to our question. It asked us to find the magnitude. Now, magnitude is in which form of the complex number? It's in the phasor format. However, our magnitude is in the trigonometric format. Why is it in the trigonometric format? Because it has the basic trigonometries: division, multiplication, addition. Okay? Now another problem that we're facing now is that this form is simple compared to this form. Okay, we need to find a workaround to solve this question. Okay, but before I show you how do we solve it, let me show you how to convert from trigonometric to phasor. How to convert from trigonometric to phasor. Converting from trigonometric to phasor format. Okay, the magnitude, it's equal to square root of a squared plus b squared, and the phase angle is equal to tan inverse of b over a. Okay, those are the two ways of finding the magnitude and the phase angle from the trigonometric format. Okay. Now, as I said before, that this is a complex number, but it's not as simple as this form. Okay, so what are we going to do? How are we going to solve it? We will break this number into two numbers, a numerator n1 and a denominator number 2. Okay, what is n1? n1, let's keep it green. n1 is equal to r over l, whereas n2 is equal to jw plus r over l. Now, where is the real and the imaginary part in those two numbers? R over L is the real part, so it's A1 plus J0. B is 0. Okay, there's no imaginary part. Here, W is B2, and the real part is R over L. Okay, so what is the magnitude for the first number? The magnitude for the first number is C1 equal to A1 squared plus B1 squared, according to this equation, right? Okay, so going back, let's plug in the numbers. A1 squared is what? R over L squared. What is B1 squared? It's 0 squared. Now 0 is nothing. Square root of R over L squared. The square with the square, they cancel each other, and what we're left with is R over L. Okay, this is the answer for C1. Let's do C2, the magnitude of the second number. It's A2 squared plus B2 squared. Okay, it is equal to square root of R over L squared plus omega squared. Now here we cannot simplify it. Why? Because of this positive sign. We cannot simplify it. Okay, so that's the answer for the second part, the magnitude of the second number. Now, what's the final magnitude? What is the final magnitude? It's equal to C1 divided by C2. Why is it C1 divided by C2? Let me show you why. Here we said we will break our transfer function into two numbers, right? N1 and N2. And N1 and N2 in the phasor format will be C1 E J theta 1, C2 E J theta 2. Now if I want only the magnitudes, it's what? It's C1 divided by C2. That's why the magnitude is C1 divided by C2. Now if I ask you what is the phase angle, it will be theta 1 minus theta 2. Why is it minus? Because theta 1 is a power and theta 2 is a power. Okay, let me show, if you want, let me show you a simpler example. where you will understand it better. If I give you two numbers, 2 to the power of 5 and 2 to the power of 3, what's the answer? It will be 2 to the power of 5 minus 3, right? Which is 2 to the power of 2, because those are powers. Okay? This is a side note. Okay, going back. What is C1? C1 is R over L, and C2 is the square root of R over L squared plus omega squared. Okay, this is the final magnitude. Okay, moving on to the next part of the question, which is finding the phase angle. Find the phase angle of the transfer function. Okay, phase angle is theta of JW. Who's the parent of the phase angle? The parent of the phase angle is the transfer function again. Okay, so in order to find the phase angle, we need the transfer function. What is the transfer function? It's R over L divided by S plus R over L. Let's write it down. So the transfer function is H of S equal to R over L divided by S plus R over L. And as the phase angle is in the form of JW, the first thing that we need to do is remove S and replace it with JW. Okay? Okay, great. And here, how are we going to find the phase angle? As we did with the magnitude, we will break this into two numbers, N1 and N2, because we need to find the thetas. We need to find the thetas in the phasor format. Okay? And theta is what? Tan inverse of B over A. What is N1? N1, let's keep it green. N1 is R over L, and N2 is JW plus R over L. Let's define the real and the imaginary parts of both numbers. This is the real part. The imaginary part is 0. Now notice that I'm not taking J. I'm not including J with the number. Okay, this is the imaginary part and this is the real part, A2. Now, let's start finding the thetas, the physical, the phase angle for both the first number and the second number. Now, theta is tan inverse of B1 over A1, which is equal to tan inverse of 0 divided by R over L, and tan inverse of 0 is 0. 0. Okay? For theta 2, it will be tan inverse of B2 over A2, which is equal to tan inverse of omega divided by R over L. Now we do not have numbers, so we will keep it as an expression. Okay, what is the total theta? Now, as I mentioned before, while I was calculating the magnitude, that the total theta will be theta 1 minus theta 2, okay, which is equal to 0 minus tan inverse, fix this, omega over R over L. So the final answer will be minus tan minus 1 omega over R over L. Okay, that's the final answer. Okay, moving on. Let's now find the I guess it's the maximum magnitude, yes. Find the maximum magnitude of the transfer function. What is the maximum magnitude? It's h max, right? No. Who is the parent for the h maximum? The parent of h maximum is, according to our hierarchy, it's the magnitude, right? Okay, so we need the magnitude in order to calculate the maximum magnitude. Let me copy all of this. Copy. Okay. Going back here, can we paste? Paste. Okay, it worked. Let's see, can I erase something? I never tried this. No, I can't. Anyhow, so this is the magnitude, okay? I think it will be better if I write it. It will be better if I write it. Cut. Okay, it doesn't look good. Okay. So the magnitude was r over L divided by square root of r over L squared plus omega squared, okay? Now, my advice to you is whenever you're finding the maximum magnitude, plot the magnitude, okay? This will help you a lot. So this is our angular frequency with the magnitude plot. We already know that this is a low pass filter, so it will be like this, right? Here we're having the cutoff frequency, and this is our h max. Now, this magnitude expression is equivalent, or it represents this line, okay? Okay. This is, imagine that this is the y, and this is an expression with the x. If I give you a line graph, and I tell you to find the x value of an expression, certain expression that has an x, what are you going to do? You are going to substitute in the value of y. But if I give you y and tell you to find x, what are you going to do? You're going to, if I give you the x value and I tell you to find y, you will substitute in the x value, right? And vice versa. It's the same thing here. What do we need to find? We need to find the maximum magnitude, which is the y-axis. Now, in order to find the y-axis, we need to substitute into the expression the x value, okay? So here, we need to find h maximum. In order to find h maximum, we need to substitute in the x value. What is the x value? The x value is 0. So here, what are we going to say? We're going to say that h max is equal to the magnitude evaluated at which frequency? 0. And then we will substitute in 0. Now this should give me 1. Let's see if this will give me 1. Squared plus 0 squared. 0 will disappear, and we're left with r over L squared. Squared with the square root will disappear. This will lead to r over L divided by r over L, which they cancel each other out, and we are left with 1, the final answer. And we already know this, right? Because it's a passive filter. Moving on to the last part, which is finding part F, finding the cutoff frequency. Part F, find the cutoff frequency of the transfer function. Okay, find the cutoff frequency of the transfer function, which is omega c. Now, who's the parent of the transfer function? Let's check it out. the parent of the transfer function, not the transfer function, the cutoff frequency is the magnitude. So we need the magnitude in order to find the cutoff frequency. The magnitude is the same. Okay, so here the magnitude is equal to R over L divided by square root of R over L squared plus omega squared. Okay, now also when finding the cutoff frequency, my advice to you is to draw the magnitude plot. Okay, now as this is the low pass filter, let's see, we are looking for the cutoff frequency, right? At the cutoff frequency, what is the magnitude? We are looking for the x value. So in order to find the x value, we need to substitute in the y. What is the y at the cutoff frequency? We said that it's always equal to h max divided by root 2. And we already found that h max is 1. Okay? So here, we are looking for omega c, which is this. Okay? Great. So here I am evaluating the expression at omega c, which will be equivalent to h max divided by root 2 equal to R over L square root of R over L squared plus omega c squared. Okay? Now, we already found out that h max is 1. What are we going to do next? We will cross multiply. Whenever you reach this step, cross multiply. Okay, before I proceed, let's say in the question said find the cutoff frequency, and it did not say, like in the previous part, find the maximum magnitude. Can I substitute in 1 directly? Yes, we can. Okay, at the end of the day, you're not going to figure out everything again. Okay, so after we cross multiply, we will get 1 multiplied by square root of R over L squared plus omega c squared equal to square root of 2 multiplied by R over L. Okay, next step is to square both sides. This will give us R over L squared plus omega c squared equal to 2 R over L squared. Next, putting this into the other side will give us omega c squared equal to 2 R over L squared minus R over L squared. How are we going to solve this? Simple. Consider it as 2x squared minus x. It's 2x squared, minus x squared. So it will be what? X squared, right? So the answer is R over L squared, and here we're having an omega c squared. The next step is to square root both sides, and you will get the final answer to be omega c is equal to R over L. Now, the question is this the right answer? Yes, of course. Why? Because we already saw that in the transfer function, omega c is what? Omega c is R over L, which shows that our answer is correct. Okay, great. Now we're going to stop here, and we'll continue to the high pass filter in the next part. Okay, the next video. Thank you.